Hey folks, how's it going? Mr. Mitchell here. In this video we're going to look at deriving an expression for potential energy for an object undergoing SHM. So let's get started. Now we've already seen in the previous theory video how to derive an expression for kinetic energy for an object undergoing SHM, which remember you could be asked in the exam, but we're now going to look at how to derive an expression for potential energy. And this one you don't actually need to be able to do in the exam, you just need to be able to understand how we get this relationship. So it says first of all, by conservation of energy, the total energy of the system at any given time is given by the sum of the kinetic and potential energies. So that means we can write quite simply that the total energy is equal to the kinetic plus the potential energy at any time. And at y equals 0, the equilibrium position, remember we're going to have maximum kinetic energy, which is the total energy of the system, but we're going to have no potential energy at that point. So that means we can take our kinetic energy equation from the previous theory video that we derived, Ek equals a half m omega squared times a squared minus y squared, and we can sub in y equals 0 to get just a half m omega squared times a squared, and that gives us the total energy at the y equals 0 point. And we can say that this is equal to the whole kinetic energy expression, a half m omega squared times a squared minus y squared from the relationship sheet, and we can then say plus EP, and we're trying to find what EP is. So if we expand this term on the right hand side, we end up with a half m omega squared a squared is equal to a half m omega squared a squared minus a half m omega squared y squared by just multiplying this half m omega squared by each of these two terms in the brackets. And then we can add the EP on the end there, and then you can hopefully see that we've got a half m omega squared a squared term there and a half m omega squared a squared term there. So we can actually just cancel these terms out and then add on a half m omega squared y squared to the other side, and we get this expression here for the potential energy of an object undergoing SHM. EP equals a half m omega squared y squared. And notice how this is different to the kinetic energy one from the previous theory video, which was this one here. Ek equals a half m omega squared times a squared minus y squared, and we're comparing that to EP equals a half m omega squared y squared. So this one's a wee bit simpler for the potential energy. And the symbols have their usual meanings. So EP is the potential energy, m is the mass of the object in kilograms, omega is angular frequency in radians per second, and y is the displacement of the object in meters. Lastly, it says we said earlier that an object will have zero potential energy when it passes through the rest position, so a quick check for this equation is to see that when y equals 0, EP equals 0, i.e. at the equilibrium position or rest position y equals 0, if we sub in y equals 0 here, the whole thing just becomes 0. So this expression confirms that the potential energy should be 0 when y equals 0 at the equilibrium position. And just remember, you don't need to be able to derive this, you just need to be able to use the equation in questions. That's all for this video folks, thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a like, subscribe to the channel, and I'll see you in the next one. Take care.